Good morning, gentlemen. Okay, so with reference to the the comments that were made on the structural drawings, I needed to verify the response. I wanted to show a verification of the required thickness for this cantilever that is in excess of 2.5 meters. This is about 2.614 meters. So what I had to do is to develop the structural analysis model for this floor. So this is the first floor layout. This is the native file of the first floor layout. So I developed the structural analysis model. So this is structural analysis model now for the first floor layout. My concern now is to verify the cantilever requirements for the slab at the west side of the building to ensure that the thickness, the deflection of the cantilever during construction and post-construction meets the code requirements. So what I did was to model the entire first floor structural layout, as you can see on the screen, using the information provided on the structural drawing. Then, so I went further to estimate the loads on the slab. So my concern is the slab. So using the loads provided initially on your load estimation. So for this, so rather than 300 millimeter thick, it was changed 175 millimeter thick. So the self-weight of that, which is about 25 times 0.175, 4.375. Okay, so this was applied on that slab. Then those that are 150 millimeter, the weight was applied. Then so the weight of plaster and then suspended mechanical and electrical services. So 0.44 plus 0.5, 0.94. Okay, so 0.94 was also applied on the slab. Then finally, the weight of the handrail. So the handrail glazing was also calculated and applied on the slab correctly. So what was calculated here was not the correct weight of handrail. So the weight of the handrail was calculated correctly and then applied. So this is not the way the weight of the handrail is to be calculated. So if you look at this, for 25 millimeter glazing, rather for 12.5 millimeter glass, you have the self-weight with 31.7 kilogram per meter square. Right, so 31.7 times 0.00981 will give me about 0.3109 kilonewtons per meter square. Then if you multiply by the height of the handrail, so I look at the architectural section. Okay, so I assume this height to be about 1.5 for a worst case scenario. So if you multiply that by 1.5, it then gives you the distributed load. Okay, so the weight of the handrail was calculated and then applied on the various joints. So I then carried out the combination based on the structural limit state requirement and then the quasi-static combination based on the code requirement. So the code specifies that to calculate deflection of beams and slabs, the quasi-static combination has to be, so the appearance of and general utility of a structure could be impaired when the calculated sag of a beam, slab, or cantilever subjected to the quasi-static permanent loads exceeds span over 250. So this is deflection limitation based on the quasi-static, or rather the quasi-permanent combination. So what is the quasi-permanent combination? So quasi-permanent combination Okay, so for serviceability limit state criterion, there is the characteristic combination of actions to be used, there is the frequent combination of actions to be used, and then there's a quasi-permanent combination of action to be used. So quasi-permanent combination is used when you're checking for cracking, checking for things like deflection and other requirements for designing bridges, and there's a certain category of vibration to be checked on the bridges. The code will specify that you need to use the quasi-permanent combination. So the specification here, the quasi-permanent combination is actually used in determining the long-term effects of external actions on a structure, the long-term behavioral effects such as irreversible deflection on a structure. That's when the quasi-permanent combination is used. If you look at here, the code specifies that the quasi-permanent combination is normally used for the long-term effects and appearance of the structure. So that's why the code specifies that for deflection evaluation, you need to use the quasi-permanent combination. Now, it says for the quasi-permanent combination, you need the dead load plus the pre-stressed load. We are not using pre-stressed, plus the summation of the representative value of the variable action times the variable action. Now, phi 2 is so for building structure, this is a domestic residential building which falls under category A for year 1991-11. So residential buildings, phi 2 is 0.3. Therefore, the combination is dead load plus 0.3 times life load. So we go back to the combination. So I define that load combination. So you have dead load, that's load case 1 and load case 2, 1.0, that's the partial factor of safety. And then for the life load now is 0.3 times load case 3, which is the slab imposed loads that take care of the loads on the slab. So I then perform the analysis and go to post-processor. Now, at the conclusion of analysis, something is interesting to note. Now, this is a 175 millimeter thick slab. Right. So, if we look at the deflection, the maximum deflection on the slab, we see, so the maximum deflection is shown here. Right. So if you look at the maximum deflection of the slab is on the 2.66 millimeter cantilever, and this deflection is 6.298 millimeters. 6.298. Now the code states that the deflection limit should be, the deflection should not exceed span over 250. Now what's the span of the cantilever? 2.614 all over 250. That's about 10.456 millimeters. So the limiting deflection is 10.456 millimeters. And then we have 6.298 millimeters. So 175 millimeter thick slab is very satisfactory.